Welcome to lesson 6. Here we're going to work on applying the mean value theorem, the first derivative test, and the second derivative test, solving some AP style questions, so some slightly more rigorous questions. So one of the most helpful things that you can do to go quickly through tricky problems is to know the different theorems, the different tests very, very well. In other words, to really understand what they are saying, how they work, why they work. And in order to do that, you need to practice recalling these things without the use of your notes. It'll feel very frustrating because you'll assume you're just getting it totally wrong. It'll feel weird. But then when you go back and you then correct your answers, you'll find that you'll actually be helping yourself remember much, much better than if you were to just look at your notes right away. So go through these A through E, answer these on your own first, and then quickly go back and take a look at your notes, correct your work. This is going to be a pretty short video from here on out, so take your time with this. Okay, first thing, the mean value theorem. To put it very succinctly, the conditions that are required are that the function is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Then, if that's the case, what the mean value theorem tells you is that if you look at the average rate of change between the endpoints A and B, there's got to be at least one point along your curve where the instantaneous rate of change, in other words, the derivative at that point, is equal to the average rate of change. For part B, explaining what it means to be concave up or concave down, what you're thinking about is not just whether the function is increasing or decreasing, but now whether or not the slope is increasing or decreasing. So if your function is concave up, that means that your slope is increasing, meaning your derivative is increasing, and therefore the second derivative is going to be positive on that interval. And then if it's concave down, you're thinking about your derivative decreasing. In other words, the second derivative, which models the rate of change of the first derivative, will be negative. First derivative test is a pretty simple one. What we do is we take a look at the first derivative and we ask ourselves, where is it going to be increasing and where is it going to be decreasing? So we find all the critical points. That's the points where the first derivative does not have a sign. In other words, it's either 0 or undefined. And then on the intervals in between, we determine whether it's positive or negative. And the first derivative test is just a succinct way of telling whether or not a point is a relative extrema based on the sign of the first derivative. So whenever your first derivative is switching from a switching sign, either from positive to negative or negative to positive, we'll have a relative extrema. And the first derivative test says if it switches, of course, from positive to negative, then it's a relative maximum, and if your derivative is switching from negative to positive, it's going to be a relative minimum. At an endpoint, there's some slightly different criteria. For a right-hand endpoint, as you are approaching from the left, if your function is increasing, that means that right-hand endpoint is a relative maximum. If you're decreasing as you approach that right-hand endpoint, your function is going to be at a relative minimum at that endpoint. And then it's the opposite for the left-hand endpoint. Since there's nothing happening to the left of it, you're considering what's going on as you move to the right from that endpoint. So if your function starts increasing as you move to the right of that endpoint, you're going to be at a relative minimum. And if your function starts decreasing as you move to the right from that endpoint, then your function will be at a relative maximum. Second derivative test is one that is nice and easy if you can take the second derivative. So if you can take the second derivative easily, then in order for a point to be a relative extrema, what you need is that the first derivative is equal to 0 at that point. And then if you have that point, that critical point where the derivative is equal, the first derivative is equal to 0, then if you look at the second derivative based on whether the second derivative is positive or negative, meaning whether it's concave up or concave down, you will be able to determine whether it's a relative max or a relative min. And last but not least, a point of inflection is where your function, original function f, is changing between, it's changing its concavity between concave up and concave down or vice versa. And that, of course, is determined by the second derivative. So when your second derivative is positive, your function is concave up, negative, concave down, and therefore when your second derivative changes sign, you're at a point of inflection. So The useful tool that we use to make that happen is, of course, a sign chart for our second derivative. And one thing that is important to note there is that when you're creating that sign chart, when you find that the second derivative is positive or negative, you want to get in the habit of writing in that interval what that means about your original function. So if your sign chart for the second derivative, you have an interval where it's positive, you want to write below there that that means that the original function f of x is going to be concave up on that interval. All right, so with that in mind, let's go ahead and take a look at a couple of slightly more complex problems that require us to know these different concepts really, really well. All right, so this problem says, at how many points on the interval from a to b does the function graph below satisfy the mean value theorem? So go ahead and pause the video here, copy down this question, give it a try on your own, go back through your answer, check it once, and then we'll talk about it. Okay, so remembering that the mean value theorem tells me if I have an interval a to b and I look at the average rate of change between that interval, then if there's a continuous function between those 2 points, that at least one time on that interval from a to b, the continuous function will have an instantaneous rate of change that is equal to the average rate of change. And the way to visualize this is to think about the slope of the secant line between a and b, because the slope of that line is the average rate of change. So we're looking for another place along my curve here that will have the same slope. In other words, where the tangent line will be parallel to the secant line. So one way to think of this is to notice that if we are traveling along this line, the secant line here, we get to a point where the secant line intersects the green curve before getting to the point B. So notice that between A and the point at the origin, we can apply the mean value theorem again. This point right here. And if we apply the mean value theorem between A and the origin, the slope that we'll be finding along this part of the curve will have the same slope as the secant line. So there's got to be some point in between A and the origin along my curve that has the same slope as the average rate of change, where the instantaneous rate of change is the same as this average rate of change. And then I can do the same between the origin and the point B. Again, the average rate of change here is the same as the average rate of change between A and B. And so somewhere along this portion of the curve, we'll again have a tangent to the curve that is parallel to this secant line. So there are 2 places along this curve where the mean value theorem is satisfied. In other words, where the instantaneous rate of change will be equal to the average rate of change along A to B. And the key thing to take away here is that when you're thinking about the mean value theorem, there's not just one value of C that works. We could have multiple, and we've actually seen examples of that before, so that's something that you want to be on the lookout for. So one way to tell is when you draw your secant line, as we have here, to take a look at the curve and break it up into chunks. Are there places where the secant line intersects the curve before getting to the endpoint? And then, in that case, you can then apply the mean value theorem between these 2 points, and the secant line will have the same slope between those 2 points as it does between the 2 endpoints. Okay, for what values of k does the function below have a relative maximum at x equals 1? Go ahead and give this a try on your own. I recommend thinking about both the first and second derivative tests, and perhaps choosing one to utilize in this situation. Okay, so when I'm taking a look at this function, I notice a couple of things. The first is that if I wanted to use the first derivative test, I'm going to have to create a sign chart for my first derivative, and then I'm going to be evaluating my derivative at some, for some value k somewhere along, the x-axis. In other words, it's going to depend on k. So I might think, okay, well, maybe I could use the second derivative test because I know exactly the x value that I'm dealing with. And the second derivative test is very easy to use in that situation because I don't have to look at a sign chart. I literally am just comparing or taking a look at the second derivative at this particular point. So I'm going to go ahead and write down the criteria for the second derivative test so that I can then make sure I satisfy both in order to determine the value k. So for the second derivative test to confirm a relative maximum, I need the derivative at c to be equal to 0, and I need the second derivative to be less than 0. In other words, I need a point where the instantaneous rate of change is 0 and the function is concave down, so that way I know on either side of it that it's going to be a smaller value. Now, in this particular situation, I know the c value I'm considering. I need c to be 1. So in this case, I need to make sure that f prime of 1 equals 0 and f double prime of 1 is less than 0. So now all I have to do is take my derivative, make sure that the derivative at 1 is equal to 0, and then take my second derivative and make sure the second derivative at 1 is less than 0. One quick note, I have to take the derivative of this function before I plug in 1, and that should be fairly obvious. I have to have a derivative first before I can substitute in 1. If I were to substitute in 1 to my function and then take the derivative, remember if I plug in 1 for x, I'm just going to get a constant value, and so the derivative of that would be 0. Just a quick thing to remember. So now taking the first derivative, k times x, well that's x to the first, I use the power rule. I have k minus 3x squared, so the derivative of that will be negative 6x. And then taking the second derivative is going to be, well, here k is a constant, so the derivative of k is 0, and the derivative of negative 6x is just negative 6. So those are my derivatives, and now I need to satisfy each of these criteria. So I let y prime of 1, which is equal to k minus 6 times 1, and I set that equal to 0. And that tells me that k has to be equal to 6. Now, at this point you're saying, okay, well how do I know what k is already if I haven't worked with my second derivative yet? Well, we need the second derivative at 1 to be less than 0. Well, the second derivative is always the same. It's always negative 6. This function is always concave down, right? It's a parabola. So I don't even need to go on to my second derivative. I've satisfied this criteria for the second derivative theorem, second derivative test. And I just know that if my k value is 6, I'll have also satisfied the first derivative portion of my second derivative test. So k will need to be equal to 6. And you could plug k in, you could take a look at the graph, and you could confirm that for yourself. All right, so with that being said, let's go ahead and talk briefly about a couple of things that you want to do just to make sure that you're working as efficiently as possible and also as correctly as possible on some of these more challenging questions, and then you can go ahead and get started on the homework. Okay, so if you're finding that it's, you kind of get stuck with some of these trickier problems, here are a couple things that I do sometimes to help myself get started. So if I've run across a problem where I'm pretty sure I need to utilize some theorem, some test, some definition, mean value theorem, whatever it may be. First what I do is I ask myself, what is it I'm trying to figure out / conclude? So in that example of the mean value theorem, I wanted to conclude that the mean value theorem worked on a certain interval. So what I did was I went ahead and went through the conditions that I need to satisfy the mean value theorem, and then looked at my function and said, okay, where is that met? Once I've done that, I synthesize what I already know from the problem. So for example, in that second problem, I already knew that the x value that I was considering was x equal 1. And so I want to then compare that information that I already know with what I need to conclude. And that sort of helps me see, well, what do I need to do moving forward, right? What is it that I'm going to need to figure out? What is it I'm going to need to solve for? In that second problem, we saw that what we needed to solve for obviously was k, such that f prime of 1 equaled 0 and f double prime of 1 was less than 0. But these are just a couple of things that can be helpful. For the most part, just staying organized, clearly identifying the type of answer you're looking for. And most importantly, for multiple choice questions, not looking at the question first. I cannot stress this enough. Not looking at the answer first. Looking at the choices first will only confuse you further. So what you should do is go ahead and try the problem, get an answer on your own first that you're confident in. Then look at the answer choices and find your answer. Now, if you notice that the answer forms are different than your answer, you can try simplifying your answer to make it look like one of the answer forms. But you should only do that after you've come up with your answer. All right, at this point, go ahead and work on Unit 4.06 homework. Remember, this is going in the grade book as a presentation grade, and you should be ready to present these problems. Email me if you have any questions.